Matrices function as active, interlocking mechanical components. They perfectly lock together to form a new structure or reject one another based entirely on structural compatibility. These grids provide the mathematical language for executing linear transformations. They map coordinate spaces and translate geometric logic into computable mechanics. Modern engineering requires modeling physical actions that happen in sequence. Whether a satellite is rotating or a voltage is dropping across a circuit, engineers need a framework capable of tracking successive, compounding changes. Matrix multiplication acts as the engine for this systemic composition. It governs how complex systems interact and how physical reactions cascade across structural disciplines. Some operations leave the base structure intact. Matrix addition and scalar multiplication are uniform, element-wise scaling operations that preserve the original geometric vector space. Multiplication is different. It is strictly governed by the inner dimension constraint, a prerequisite that must be met before two distinct systems can interact. Placing an M by N matrix next to an R by P matrix, multiplication is defined only if the inner variables, N and R, are exactly equal. This structural adapter maps the first system's output to the subsequent input, merging them into a single M by P entity. If those inner dimensions do not match, the math halts. This mismatch indicates that the structural link between the two system states is physically impossible. When parent matrices are compatible, calculating the resulting matrix requires a specific mechanical process. This dot product equation defines the movement. A row from the first matrix sweeps horizontally, while a column of the second sweeps vertically. The interacting elements are summed and deposited into a resulting cell. Iterating this across every combination populates the new grid. Because of this sweeping mechanism, matrix multiplication is non-commutative. Multiplying matrix A by matrix B produces a different result than multiplying B by A. In physics, this rule enforces chronological sequence. A 90-degree rotation on the x-axis, followed by the y-axis, places an object in a different final position than rotating on the y-axis first. The non-commutative operator dictates the chronological timeline of compounding physical events. This timeline logic is absolutely critical in the field of aerospace engineering for tracking kinematics and precise vehicle orientation. Spacecraft orientation is tracked using direction cosine matrices. These map successive rotations around the vehicle's localized body axes, yaw, pitch, and roll. This compounding rotation equation tracks those movements. As the RY matrix multiplies against the RX matrix, the axis system updates to reflect the new orientation. Multiplying these operational matrices compounds the sequential angular updates into a single orientation state. Non-commutativity remains the absolutely vital constraint here. Calculating the x-axis rotation before the y-axis rotation models a completely different physical trajectory. Aerospace systems depend on strictly ordered multiplication to prevent spatial drift and definitively capture the physical attitude of the craft. These same mechanics dictate signal flow in electronics, particularly when analyzing complex linear networks and circuit cascades. Circuit components are defined as two-port networks using transmission parameters. Each component matrix maps an incoming voltage and current directly to an outgoing state. This series cascade equation maps an input factor to an output factor through a sequential line of interconnected components, represented here as T1, T2, and T3. The overall transmission matrix of the entire system is found by compounding the individual matrices of each component in the sequence. The inner dimension constraint dictates the physical reality of the circuit. The mathematical requirement that N equals R ensures the electrical output of T1 aligns with the expected input of T2. Matrix cascade equations fundamentally guarantee that signal data and power transfer securely across modular networks without any loss of continuity. In computing and modern game engines, strict matrix constraints directly manage how 3D assets are transformed and projected onto viewports. Every geometric vertex moves through a coordinate pipeline. First, they undergo scaling matrices, then they pass through rotation, and finally translation matrices. This specific transformation equation fundamentally modifies the state vector right to left, precisely compounding the model, view, and projection operations in sequence. To satisfy the inner dimension constraints for all these operations, software engines use 4x4 homogeneous coordinates, representing every transformation uniformly. Modern GPUs take this linear transformation process and execute it simultaneously across millions of vertices using massive parallelization. Stacking these strictly non-commutative matrices transforms algebra into a rendering engine capable of projecting complex virtual worlds in real time. Theoretical equations must be executed within the practical reality of software engineering and simulation. When building digital models, whether simulating a spacecraft or a circuit, software must explicitly track those internal dimensional boundaries. This snippet shows a standard safety net. Developers write exception handlers to capture invalid structural inputs before they can propagate through the system. An uncaught dimensional mismatch in a script means the system physically breaks. The simulated physics begin to drift, or the program simply crashes. Code-level tracking enforces the mathematical rules to prevent structural failure in engineering pipelines. The systems we have explored, spacecraft tracking, electronic component cascades, and GPU rendering, share a common core. These disciplines operate with different physical variables, yet they rely on the same structural matrix equations to function. Inner dimension matching builds the links between states, and non-commutativity enforces the passage of physical sequence. Matrix operations allow engineers to model, scale, and reliably construct the systems that define our physical and digital reality.